Okay, most of what we've been talking about in this chapter so far is review. In this section, we're going to take the plunge and leave the domain of positive whole number exponents and give concrete meaning to zero, negative, and fractional exponents, and in fact, extend them to the idea of any real number exponents. Okay, so let's see how we're going to proceed to do that. So we started with the definition for positive whole number exponents, where we have x to the n would be n factors of x. Okay. From that, we derived several properties, such as x to the a times x to the b is equal to x to the a plus b. Okay, and x to the a raised to the b power is equal to x to the a times b, and so forth. There were 5 of these properties we came up with. So these properties characterize the way exponents should behave, and so what we want to do is to say, how can we assign meaning to exponents that are not counting numbers? So I'm not going to think of it as counting how many factors anymore. Let's just look at numbers that obey these properties. Okay, so let's do an example here. Let's look at what x to the 0 could possibly mean. Okay, to say there are no factors of x multiplied together leaves it a bit ambiguous. Is the answer going to be 0? What is it going to be? Okay, let's use the properties of exponents to give meaning to this construct here, x to the 0 power, whatever it means. This is so far an undefined quantity. But look at this first property for exponents. It says that x to the a times x to the b should equal x to the a plus b. So x to the 0 times x to some other power, let's call it b, is going to equal x to the 0 plus b. Well, what is 0 plus b? That's simply x to the b. Okay, look what we have here. Here is a number, whatever it is, which when multiplied by x to the b equals x to the b. What number do you know of that fits this description? Well, there's only one such number. This would make this an identity for multiplication. Something times x to the b leaves that unchanged. That's what you mean by the multiplicative identity, 1. So, the only meaning that is possible to give to x to the 0 that would make it consistent with the properties of exponents would be if x to the 0 equals 1. Okay? So this is going to be our definition when the exponent is 0. When the exponent is 0, we define it so that x to the 0 is equal to 1. Okay? Let's see how this fits with our graphical understanding of an exponential function. Okay, I've plotted the curve f of x equals 2 to the x power, and I've put 3 points on this using integer exponents. So when x is 1, 2 to the 1 is 2. Okay, that's right here. When x is 2, 2 to the 2 is 4, and when x is 3, 2 to the 3 is 8. Let's plot the point 0 and then 2 to the 0 by the definition we've just established. So I'm going to put here 0, comma, 2 to the 0, which is 1. And there we are. So notice that that fits not only with the properties, but it also fits with this curve. So it helps to fill out this curve. Okay, let's go on. How would we define negative exponents? Well, again, let's go back to our properties. X to the minus n, whatever that means. So far it's an undefined quantity. But if I multiply it by x to the n, the properties that we've learned are that we should add the exponents. So what is n added to a negative n? It would come out x to the 0. But we've just established what x to the 0 is. That's equal to 1. So here we have something which, when multiplied by x to the n, is equal to 1. Well, let's solve for the box. The box is equal to, divide both sides by this. It's 1 over x to the n. So we can say that x to the minus n is equal to 1 over x to the n. Okay? So, in other words, putting a negative on the exponent basically changes it into a reciprocal. Let's look at some concrete examples of this. Let's look at x to the minus 1. That would be 1 over x to the 1, or simply 1 over x. X to the minus 2, 1 over x squared, and so forth. Okay? X to any negative power would be the reciprocal of x to the positive version of that power. Let's see how this definition works on the graph as well. Okay, let's plot the point minus 1. And if x is minus 1, our function here is 2 to the x. So what is 2 to the minus 1? Well, what we've just established, it should be equal to 1/2. Okay, so it's the reciprocal of 2 to the 1. So 2 to the minus 1 would be 1 over 2 to the 1. And there we have it. So it fits. How about minus 2? So I'll put minus 2. Then the y value would be 2 to the minus 2, which would be 1 over 2 raised to the second power, 1 over 4. Okay, and there we have it. So here we have the values. Minus 2 is 0.25, minus 1 is 0.5. So you can see these fit, and again, we are continuing to fill out this line. Let's continue again. Okay, so what could we possibly mean by x to the 1 over n? So a fraction, we're going to limit ourselves for the time being to fractions as 1 over some number, okay? Well, let's use the property that x to the a raised to the b power is equal to x to the a times b. And let's see where that would lead us. Well, if I take x to the 1 over n and raise it to the nth power, what this rule says is I should multiply the exponents. I should get x to the n over n, but that's just 1. That's just equal to x to the 1, which is simply x. Okay, so what this is telling us is that x to the 1 over n, whatever that is, when I raise it to the nth power, I'm going to get x. Well, what do you call a number which, when raised to the nth power, gives you x? This is the very definition of the nth root of x. Okay, so the nth root of x. Okay, let's use some concrete examples here. What about x to the 1/2? Well, this would be the nth root or the square root of x. Okay, x to the 1/3 would be the cube root of x, and so forth. So any root here, square root, cube root, fourth root, etc., corresponds to a reciprocal exponent. So a 1/2, 1/3, 1/4, etc. Okay. Let's look at this a little differently. What if I took x to the 1/2 times x to the 1/2? Let's use the other property of exponents that says we should add the exponents here. This would be x to the 1/2 plus 1/2, or x to the 1, simply x. So this means that this number times itself gives us x. Again, we see that this number should be the square root of x. Okay? What if I take x to the 1/3 times x to the 1/3 times x to the 1/3? Well, if I add the exponents, it's going to be x to the first power, or just x. So here's a number which, when multiplied by itself and again by itself, gives us x. That's the very definition of the cube root of x. Okay? So whether we look at it this way or whether we look at it using this property up here, we can see that a reciprocal exponent is equivalent to a root. Let's see how some of these fit on the exponential curve we've been generating. Okay, let's start with 1/2. So I'm going to take 1/2 or 0.5, and then 2 to the 0.5 power. Well, 2 to the 1/2 power should be the square root of 2. So I'm going to put here square root of 2, SQRT of 2. And there we go. It's right on the curve. Okay? Let's try another one. Let's try 1/3, comma. And what about 2 to the 1/3? Well, 2 to the 1/3 should be the cube root of 2. Well, we don't have, I don't believe we have a cube root function. Let's see if we do. CUBERT. Nope, nothing like that. We don't have a cube root function, so let's take the cube root of 2 using a calculator and just feed it in. If I take 2 and then use shift with the exponent, it comes out a root. Okay, and then I'm going to say 3, so that's the cube root, equals. So it comes out 1.2599. Okay, so over here I'm going to say 1/3, comma 1.2599. And there it is. It's right there on the curve. Okay, and we could continue doing that. So these definitions appear to be working. Let's go on to more general fractions. Okay, what about x to the a over b? Well, x to the a over b could be written x to the a times 1 over b. So a number times a reciprocal type fraction would be the same as a over b. This, we have learned, is the same as x to the a to the 1 over b. The power of a power rule says that x to the a to something else is x to the product of these two, which is a times 1 over b, which would be x to the a over b. Well, this we can interpret because we know how to take reciprocal exponents, and now we have a reciprocal out here. So this is equal to x to the a, and then we take the bth root of that. Okay, so that's our definition of x to the a over b. So the a would be the power and b would be the root. But there's a different way we could have done this. Instead of saying a times 1 over b, I could write a to the 1 over b times a. In other words, I could write these two factors in reverse order. And that's the same as x to the 1 over b raised to the a power. Well, we know what x to the 1 over b is. That's the bth root of x. And we can take that to the a power. Okay, so what do we have here? When you have x to the a over b, in either of these cases, this is going to be the power, and this is going to be a root. Whether we take the power first, x to the a, and then take the root of the result, or whether we take the root first and then raise that to some power, it doesn't really matter. These are equivalent. Okay? You're free to interchange. If you have a root of a power, I can express it as a power of a root, and these are equivalent. Okay? Okay, when we've gotten to this point, notice what we've accomplished. I can express any rational number as a ratio of two integers. And if I know how to take x to a rational exponent, it means I can fill out the number line very densely. So between any two rational numbers, there's another rational number, and you can go in as tightly as you like. And in fact, even when we talk about real numbers, we're sort of talking about an idealistic situation. So what if I take something that's clearly a real number, not even a rational number? What if I take x to the pi? Well, if I write this out, it would be x to the 3.14159, and you're going to have to stop somewhere because you're not going to continue infinitely. Now, pi itself is an infinite non-repeating decimal, but typically you write it out to some degree of precision and then stop. So we're really approximating pi to whatever degree of accuracy we like. So rational numbers can be used to approximate any real number to any degree of precision. Notice that this rational number can be rewritten as the ratio of two integers. This is the same as x to the 314,159 over, let's see, 1, 2, 3, 4, 5. Okay, so if I divide this by 100,000, it's 1, 2, 3, 4, 5. That brings it back to 3 point. Okay, so this would be the same as saying x to the 314,159 power, and take the 1, 2, 3, 4, 5, take the 100,000th root of x to that power. Now, this is not a practical way to do the computation. However, your calculator knows how to work directly with exponents in this form. And so you could take x to the pi power using the approximation of pi that's stored in your calculator, and you should be able to get a perfectly reasonable result. Okay, let's try fitting a couple of numbers of this style onto our exponential graph. Let's come back here to the function f of x is 2 to the x, and I want to try 2 to the 3/2 power. Okay, so I'm going to let x equal 3/2. So if I take 3/2, or I could have said 1.5, that would be good too. And what we've learned is that that's equivalent to raising 2 to the 3rd power and then taking the square root. So I'm going to take the square root of 2 raised to the 3rd power. And there we are. It's right here, and it fits the curve. It turns out that any fractional exponent, any rational exponent you want to choose, you should be able to find its location here on this curve. Okay. Since any number on the number line can be approximated as a terminating decimal, we should be able to plot any rational exponent, which gives us this smooth curve to start with. But the real values are approximated as close as we like. So let's see where 2 to the pi is. I'm going to take my x value, so 2 to the pi, okay? The x value is going to be pi, so I go Alt-P, by the way. That's the way. I could use this little thing over here and select pi, but Alt-P would also do it, okay? And then I'm going to write comma, and then 2 raised to the Alt-P. So pi, comma, 2 to the pi, and this is j. That's not on the scale here. Let's go down there. That's where it is, okay? That's 8 point something, 8.82 it was, all right? So let's just do that. Okay, so even something that looks like a real number, realize that represented internally in the computer, even pi is approximated as a rational number. And we know how to interpret rational exponents, and we know how to compute rational exponents. We have a way of computing rational exponents now. We can take a power combined with a root, and we can find any rational exponent we want. All right? So in the future, if I wanted to say 2 to the pi power, for instance, I would say 2 raised to the, and then say shift pi power equals, it'll just compute it. So you don't, in practice, have to go through the two-step process because your calculator has algorithms for doing all of that built in. Bottom line, we now have extended beyond the definition for repeated multiplication, which worked for counting numbers only. The curve we've come up with fits all the counting number exponentials, but it also fits any rational exponential, including zero, including negatives, including reciprocal fractions, and in fact general fractions. Okay, that was a big step forward for this one section.